So if we rewind the tape to Friday, Friday we did a lot of talking about radioactivity. And we ended with talking about the three different types of radioactive decay: the alpha decay, the beta decay, and the gamma decay. We're going to keep talking about those, but in slightly different forms as we start to go off of just simply what is it to talking about the actual dangers associated with it. So, the first thing that we want to talk about is penetration. Penetrating power for these different radioactive particles varies by particle. And as I mentioned in Friday's lecture, the size of the particle does have a lot to do with its penetrating power. The bigger it is, the less quickly it moves, the more likely it is to be blocked by simple materials. So alpha particles, which are the heaviest of particles. Remember, your alpha particles are essentially helium nuclei. 2 protons, 2 neutrons, no electrons. Those suckers are huge. And even though they travel at a decent sized speed, their size does present certain issues. They don't have the energy necessarily to go through and penetrate through really much of anything. So things like your skin can block alpha particles. Your clothing can block alpha particles. Things as simple as a sheet of paper can block alpha particles, at least in small part. Now, Friday in lab, you're going to see a lot of this in action when you do the radioactivity lab, because you're going to get to play with a small sample of an alpha emitter, a small sample of a beta emitter, and see what kinds of things can happen in terms of some of the concepts that we're going to talk about this week. Where we have to be particularly concerned with alpha particles, however, is because of their size. If it somehow made its way into your body, your internal organs do not have the thick kind of barrier on them that your skin does. Your skin provides a very good barrier to the outside world. Your organs, your internal cells don't have that barrier in place. And so if an alpha source was able to get into your body, it could do some significant damage. Beta particles, on the other hand, they are capable of penetrating your skin. Materials like paper are okay at blocking their penetration. Better sources of blocking are usually things like thin sheets of aluminum, aluminum foils, small gauge aluminum sheet metal are pretty good at blocking beta particles, and certainly lead, even in small quantities, lead and concrete are definitely viable as well. Both of these particles are considered alpha particles, or excuse me, both of these are considered ionizing energy. Ionizing energy is one where, as the energetic particle encounters things, it is capable of stripping them of electrons, and stripping of them of those electrons will end up resulting in a number of different things, but cell mutation, cell death are probably the most common of them. Gamma rays are also ionizing radiation, and because they are pure energy, there are very few things that can actually limit their transmission. So your skin is useless against gamma. Your bones are useless against gamma. They don't have the density to block the particles from transmitting. However, lead is capable of blocking gamma rays, as is concrete, if you have a thick enough concrete barrier. So The closest thing that we can kind of think of in the way of gamma rays mainly come from usually cosmic sources, like the kind of stuff that happens in the sun or in other stars. Those are the places where we see, gamma kinds of radiation, that kind of high level radiation. It's not the only place, but that's kind of the most common place. Closest thing that we have here that we can kind of think of is X-rays. Now, X-rays are not as energetic as gamma rays are, but they're close. And if you think about when you get an X-ray taken, whether it's of your teeth or of a broken bone, you'll notice that two things always happen. First thing that happens is that they put some kind of a protective barrier on you. That protective barrier is usually some sort of lead vest of some kind. And the main reason for that lead vest is to protect your internal organs from those X-rays, because the lead is capable of absorbing and blocking those X-rays from going through your body. The second thing that happens is that the technician, whoever is taking the actual picture, usually scurries behind a wall of some kind in order to take the picture. And the reason for that is, rather than have them donning a gigantic lead vest all day, usually them scurrying around that corner puts them between a concrete barrier and the actual beam of X-rays. And that provides them enough protection that they don't really see any kinds of nasty effects from being exposed to radiation on a daily basis. So in a picture kind of way, we can look at this. We can see that the alpha particles are going to be blocked by the skin. They will not even penetrate that first layer of skin. Beta particles are capable of penetrating the skin, but when they get into the denser tissues underneath the skin, they tend to be okay. They tend to get blocked there. So beta particles rarely make it to your organs either, unless, again, you ingest it somehow. Gamma radiation, on the other hand, this arrow doesn't even do it justice. With gamma radiation, we would be seeing this arrow extended, not just stopping at the organs, but going all the way through the picture. That's the penetrating power. The gamma radiation will pass through you. It doesn't get stopped along the way, it passes through you. And as it passes through you, all of these things that it encounters along the way have the capability of becoming ionized. And that's where your potential health defects come in. So the part we're going to look at next here is something called a transmutation reaction. Transmutation reaction is basically just another way of saying a nuclear reaction. Because what happens in a transmutation reaction is we have some kind of radioactive nucleus, otherwise known as the parent atom. And this parent atom is radioactive, unstable, and as a result of that unstable kind of nature, it's going to go through one of these three types of decay: alpha, beta, or gamma. When it does so, it is going to form a more stable nucleus in addition to the radioactive particle. That more stable nucleus is known as the daughter nuclide. Now, balancing nuclear reactions is a little bit different from balancing chemical reactions. Chemical reactions, we were all concerned about the law of conservation of matter. I needed every single atom that was on the reactant side to be matched up by an atom on the product side. But that's not how it works in a transmutation reaction. In a transmutation reaction, we're more concerned with two things: particles, that is protons and neutrons, and charge. And so instead of looking at atomic, or excuse me, instead of looking at, I've got this many carbons over here and this many carbons over here, what I'm going to look at instead are mass numbers and atomic numbers. So I'm still going to split the reaction in half and look at the reactants versus the products. But instead of looking at the number of atoms on each side, I'm going to look at the atomic number and the mass number. So the sum of all of the mass numbers have to equal out on both sides. The sum of the atomic numbers have to equal out on the both sides. And again, we're working off of our common system here of notation, where we've got the mass number on the top, the atomic number on the bottom, and the element's symbol there in the middle. So what do these transmutation reactions ultimately end up looking like? Well, here's a couple of examples. So for an alpha decay, this is a common example of an alpha decay. Uranium-238 turning into thorium-234 plus an alpha particle. Now, again, coming back to we have 238 on this side. We got 234 plus 4, and that equals 238 for the mass number on this side. We had 92 for the uranium, and then we have 90 for the thorium plus the 2 for the alpha particle, give 92 here in the denominator. So this is the kind of conservation that we need to be concerned with these nuclear reactions, is making sure that my mass number on the reactant side matches up with the mass number on the product side, and that my atomic number, the bottom number on the reactant side, matches up with the atomic number on the product side. These kinds of chemical nuclear reactions are quite common, and they can go across all the different types of decay, and actually can go into other kinds of nuclear equations as well. Things like bombardment reactions, that is, the reactions that ultimately generate all of those synthetic elements on the periodic table. So all the ones in this one in the room here that are white letters outlined in black, all of those are synthetic. Those were all man-made. And almost all of them were done by some kind of bombardment reaction, taking a known substance and throwing other particles at it and trying to get some of them to stick. In the beta decay, we can do the exact same kind of thing. Split it down the middle. I've got 234 on this side. I've got 234 plus 0 on this side, which matches up my mass numbers. Got 90 in the bottom, 91 plus a -1, gives me the 90 that I'm seeking over here. So an interesting thing about beta decay overall is that beta decay, because the particle is negative in charge, we end up going up the periodic table instead of down the periodic table. So for thorium, we see protactinium being formed out of that beta decay, as opposed to actinium or radium or another one of the lower atomic number elements. For gamma decay can come in a number of different forms. This is one of the forms where we can see that we had 119 for the tin on the reactant side. We have 118 for the tin on the product side, plus a neutron, plus the zero mass gamma particle. That in total gives me 119. And for the 50, we have 50 for the tin, no change in the neutron, no change in the gamma particle. So that's 50 overall. Gamma decays usually do occur without changing the element itself. So this is one form where the unstable nature of the tin 119, basically the energy of that nuclide is so great that when it ditches that energy, it also knocks off a neutron in the process. Another kind of example, however, is where we can see something like this. This star indicates an element or a nuclide that is considered metastable. That metastability, what that means is that it is stable to a certain degree, but it is not in the most stable form. So it'll sit there for an indeterminate amount of time. It's not going to immediately decay, but at some point it will decay because there is a lower energy state available to it. And when it reaches that lower energy state, it's going to give off that gamma ray as a result. So those are the two primary ways that we see gamma decay. We either see something that's metastable, that basically just relaxes to a lower energy state and gives up that gamma ray, or we see an unstable nuclide that gives away a neutron as it gives away the gamma ray. So both are possible for this kind of decay. But let's do some example problems. In this process, we want to do two things. We want to identify the missing radioactive particle and identify the process by name. Now to do that, this is kind of a game of fill in the blank. What's missing? So to do that, you're going to need a periodic table of some kind so that you can pull the atomic numbers as they come along. So for actinium, actinium is element number 89. Francium is element number 87. So to figure out what's missing, again, I need to look at 222 up top, 89 on the bottom. I've got 218 already, plus something is going to give me 222. So if I solve algebraically, x is equal to 4. On the bottom side, I've got 87 plus x, give me 89. That means I'm going to need a 2 here. This part's about recognition. The particle that gives me a mass of 4 and a atomic number of 2 is an alpha particle. And so this nuclear process is alpha K. Okay, similar process for the other ones here. For vanadium, vanadium is element number 23. Chromium is element number 24. So if I set up my marks here, I need 47 on top and 23 on the bottom. Chromium gives me 47, so 47 plus x is equal to 47. So x must be 0. And on the bottom, 24 plus x is equal to 23. So x must be -1. So I've got a 0 up top, a -1 on the bottom. Again, knowing our definitions, that's a beta particle, which means that this is beta decay. In the last one here, we've got cobalt. Cobalt is element number 27. Only thing that we've been given is that there is a neutron. The neutron has no mass, or excuse me, no charge. So from the standpoint of splitting this again, I see a 60 on the top. 1 plus x is equal to 60. So we're dealing with a 59 here. Or excuse me, 0 plus x is equal to 27. So we've got a 27 here. Element number 27 on the periodic table is cobalt. So the question here still is, well, what has happened here? We've got a neutron to shake loose. Is there anything else that could have possibly happened here, John? Yeah, so this is one of the scenarios where we can have gamma. So this one actually has two. We've got the gamma particle or the gamma ray plus the cobalt 59. So we've got a gamma decay going on here. And so as far as transmutation reactions are concerned, this is all that you really need to do. It's a matter of simple adding and subtracting. And again, it's not terribly difficult adding and subtracting because the biggest number that you're going to deal with as far as gamma or any of the particles are concerned is a 4. So if you can add and subtract by 4, you should be okay. Any questions with this? Okay, so let's get a little bit deeper into some of the protections that we will use and take for dealing with radiation and radioactive materials. So from a manufacturing standpoint, when we have radiation sources that are being shipped or transported, moved around in any kind of way, the manufacturer of the radioactive material seals them in a double-skinned steel tube. And that is usually housed within some kind of a medical device or other kind of protection. Now, depending upon what's going on, you can see one of the things that these sealed radiation sources can be used for is sterilization and disinfecting purposes. So for example, gamma radiation sources are often used to irradiate polyethylene or rubber materials. So plastics and rubbers are irradiated using gamma rays. Primary reason for this? Well, it has the same effect on insects and microbes as it has on us. If you're dealing with a population of pests, this can act as kind of like a pesticide of sorts, destroying insect cells, also killing funguses, molds, microbes. One of the places where this is used often is for the rapid irradiation of meat. So to prevent spoilage, or at least make spoilage something that it happens a lot later of a date. Radiation has been used for those kinds of purposes on produce, meat, poultry, and so on, especially those that have deadly bacteria growths associated with it, things like E. coli, salmonella, Legionella, other kinds of things. Now, if this potential kind of makes your skin crawl a little bit, the fact that you could be potentially eating meat and produce that has been treated with radiation, do be advised of one thing. This is called the Redura symbol. The Redura symbol is required by the FDA to be put on any kind of foodstuff that has been irradiated as part of its processing. So if you go down to JC's and buy a pack of steaks, first of all, let me party with you. And second of all, you're probably not going to see the Redura symbol because that's not part of the processing that is used at most grocery stores. However, if you do see this symbol, understand that that's what it means. And again, this symbol is put on any kind of food stuff. produce, so lettuces, cabbages, bagged salads, tomatoes, any kind of meat or poultry. If you see the Redura symbol, understand that that's what it means. It means that that food has been irradiated for the purposes of killing bacteria and other kinds of potential baddies on the food. Not something that's in terribly high use, even in these uncertain COVID times, but still, there has been a lot done with that kind of thing, and I guess it does pose a possibility, depending on where you live. The other thing that we want to get into for today is how do we actually measure radiation? So we've talked about what radiation is. We've talked about what kinds of reactions occur, but we haven't really gotten into how we measure it. So there are a number of different uses and units for radiation and the dose of radiation that we would encounter. And the first of these is something called activity. Activity is relatively simple to understand. It's the amount of radiation that is being emitted by a radioisotope. And we can measure our exposure to this radioactive material through a couple of things. One of them is called a film badge. The other one's called a pocket dosimeter. If you've spent any kind of significant time in a hospital, either as a visitor or a patient or some combination of the two, you probably will recognize at least one of these badges or dosimeters, because pretty much every doctor, every custodian, everybody that works in a hospital carries something like this on their person at all times. These are what the dosimeters look like that come on badges. Again, if you spend any time at any hospital, you've seen some kind of version of these. Usually are on the pockets of the person that is walking around. You might have also seen these. These kind of look like pen holders, but these are pocket dosimeters. Kind of serve the same purpose. They have a detector inside of them, measure how much radiation that person's been exposed to, lets them know if there's been too much. The advantage to these, obviously, they pin to a shirt pocket or a lab coat pocket, and so it just looks like a normal part of their clothing. And that's kind of the point, is it's something that you carry around, you don't really even know it's there, but it's there to help protect you and let you know if you've been exposed to large amounts of radiation. And same thing with this. This is the idea is this looks like an ID badge, but it also has the added benefit of having a detector in it to let you know how much activity you've been exposed to. So some other units of radiation, we have the RAD, R-A-D, stands for the radiation absorbed dose. The RAD is something that is standardized per gram of body tissue. So a RAD would be how much radiation is absorbed per gram of matter. We also have the REM. The REM is short for the Röntgen equivalent man, and it's the amount of body tissue damage that can be caused by the radiation exposure of one Röntgen of X-rays over the course of a day. So the rad standardizes to the person. The REM standardizes to a particular unit of energy, a Röntgen of X-rays. And so these two comparative values give us some idea of how much radiation's been absorbed, and possibly more importantly than that, what that is relative to other kinds of doses of radiation. We can detect radioactivity using something called a Geiger counter. You'll become very familiar with Geiger counters in the lab on Friday. You've probably had some exposure to them before. If you ever have seen anyone that's carrying around a box that makes little clicking sounds, that is a Geiger counter, or at least a lot of those are. And what the Geiger counter does is it picks up radiation because what it detects is the ionizing matter. So as radioactive materials encounter other materials, like I said before, they strip them of electrons. The Geiger counter is able to detect those ionized materials to let you know how much ionization has gone on. So the Geiger counter is probably the most common detector out there. Yes, we talked about the dosimeters, but I mean, in most cases, if you're going to be looking for radiation, a Geiger counter is what you're going to be using. And this is what that Geiger counter looks like. So again, it's a box. It's about that large. Fits relatively easy inside your hand. Used by first responders, used by others. And again, you'll use something very, very similar to this in the lab on Friday. Now, the thing about the Geiger counter is it doesn't tell us the difference between alpha, beta, and gamma radiation. It detects all of them equally. And we can do different kinds of readings. So this top reading here, the MR per hour, that's milliröntgens per hour. So that gives us more of an idea of dose. We also get counts per minute here, counts per minute and counts per second. That tells us how many radioactive particles we see in that minute of time. All right, last thing we'll talk about today. What happens when we get exposed to radiation? Well, the answer to that question is complicated. It really depends on how much radiation we actually encounter. As I mentioned on Friday, you're encountering radiation right now. Now, it's very small, trace amounts of background radiation, but it's radiation nonetheless. If I pulled out a Geiger counter right now, I would probably get a couple of clicks every, 30 seconds or so. Because background radiation is relatively small, but it's still present. So the real idea here is we have to know the dosage. We have to know how much radiation you're actually being concerned with. And so radiation level becomes important. because this is the dose equivalent rate of radiation that you actually are being exposed to. Now, regardless of what kind of radiation, if you're exposed long term to even small amounts of radiation, not background radiation, mind you, but small amounts of radiation over a long, long period of time, it does have an effect on your body. We talked about this on Friday, in particular, talking about radon. Radon is kind of a silent killer because it can be present in your house, exposing you to radiation, and you really have no way of knowing it's there without doing any kind of testing. Long-term exposure to radiation can cause your body tissues to become necrotic, means that they basically start to die in places, or they can become ulcerated, which has its own set of issues as well. We'll end with this image. This is a graphic of all the different types of radiation that you can be exposed to on a normal kind of basis. Now you'll see most of this is background radiation. So terrestrial radiation, this is background radiation. This is stuff that comes like out of the earth. Internal radiation, this is radioactive materials that just are in your body naturally as you do things that are normal, like eat and breathe and drink and sleep. Space, as I mentioned, a good chunk of radiation comes from the sun and from other solar bodies. Our ozone layer blocks a good chunk of it, but not all of it. So about 5% of the radiation that most people encounter is just stuff that you can't do much about. Radon and thoron makes up a good third plus of the background radiation that you can encounter. So you put all those together, and this is exactly half of your normal exposures to radiation. Background radiation accounts for half of the radiation that you encounter. And again, I said before, background radiation, not really anything that we concern ourselves with too much because it's very low quantity, low count. The only real concerns are if you have elevated levels of radon or thoron in your home, that's of a greater concern because those levels are elevated and you're getting more than that 37%. The others here, you can see the majority of them, about 48% of them, are medical applications. Tomography, nuclear medicines, that'd be things like chemotherapy or nuclear radiation treatments. Interventional fluoroscopies, radiographies, so things like testing. You know, if you have to do a GI scan or a PET imaging scan, they usually give you some kind of radioactive material to ingest so that they can trace it through your body during the imaging. Now, if in a normal year you don't get an x-ray, which most people get at least one if they go to the dentist, or you don't end up in the hospital, or you don't end up in any kind of imaging situation like, you know, getting a GI test or something, your individual exposures are considerably lower. But again, this is on average. This is on average. So this is going to be our parting image for today. On Wednesday, we're going to continue looking at chapter 16, moving on into some of the other things like what are some things that we can do to prevent or at least help with exposures to radiation? Things like shielding, things like distancing. So that's what we'll get into on Wednesday.